Hello. Demonstration of Poisson distribution questions in Mei S2, and I'm going to use June 2010 question 2 as an example. Well, as ever, the first thing we do is read the question. A radioactive source is decaying at a mean rate of 3.4 counts per 5 seconds. So we're working in 5-second units. Okay. See what the first question is. State the conditions for a Poisson to be a suitable model for the rate of decay of this source. Well, all Poissons, we've got two factors really, haven't we? We've got to have the same average rate throughout. There's a point for that. So number one, there's a point. Number two is events got to be independent events. Yeah, we can't have one decay kicking off another one, and that's not the case, is it, in radioactivities? That's okay. So they then go on. You may assume that Poisson distribution with mean rate 3.5 is suitable. So if you didn't know any better, then it is suitable. First part, state the variance of a Poisson distribution. Of this Poisson distribution. Well, what's the variance of a Poisson? Well, the variance of a Poisson is lambda, and they've told us here that in the equation we're doing here, I should have written just above that lambda. They've just told us is 3.4. So what we're looking at here is a variable, Poisson variable, with lambda is 3.4. So what variance going to be? Well, it's going to be equal to lambda, which is going to be equal to 3.4. How about that? Okay. Find the probability that exactly 3 counts of exactly 3 counts in 5 seconds, and at least 3 counts in 5 seconds. Okay. So what are we looking at? Well, we've got our Poisson up there, and which is one of the more straightforward ones here. We've got probability that x equals 3. Second question's asking us at least 3, so that's going to be x greater than or equal to 3, isn't it? Okay, let's do that then. Well, the first one's pretty straightforward. We can get our calculator out. Let's get it to work. Let's bring our calculator into the window. Here you go. So here's our Poisson, and the first one we want to know a particular point because it says exactly. So we're going to use our, let's just go up and pick it up, distribution, right hand end, Poisson, and we want a point. We're only in the exact value. What have we got to enter in here? Well, we've got to enter in the value we're looking for, which is 3, the occurrence of 3, with a lambda of 3.4, pushing the button. Here we go with our calculator. So our first answer is 0.2186. 0.2186. And go and equate, please, to 4 decimal places. Okay, so that was the easy bit. We got a mark or 2 for that, didn't we? Now let's have a look at the second part. At least 3 counts in a 5-second period. I'm going to move us on, and I'm going to start extending here. So this is number 3. Okay, number 2, as we just found, was for 2a was probability that x equals 3, wasn't it? Equals 0.2186. Now what have we got to find? In B, we've got to find the probability that x is at least 3. So that's that. Can't get that out of our calculator, can we? So we've got to work out 1 minus. So we could have 0 here, 1, 2, 3, 4, off to infinity there, 1, 2, 3, 4. Probability we're trying to find is greater than or equal to 3. So our complementary probability, which we can find, is this one here. So that's less than or equal to 2. So we're going to calculate 1 minus the probability that x is less than or equal to 2. How can we get this? Well, from our calculator, we're going to use our PCD function. So let's get our calculator up again, hop back up until distributions, Poisson, PCD, and now we need to change that number to 2, isn't it? So there we go, and execute here. So now we've got 3397 there, haven't we? And let's extend our page, which equals 1 minus 0.3397, which gives us a probability of 0.6603. So there we go, that was good. Those two worth 5 marks, weren't they? So far we're in for, I think, 7 marks, and we've been going 6 minutes. So, and that's with all the spiel as well. Okay, let's have a look at our next question then. Okay, let's do this in purple, shall we? Let's go to yellow. Right, find the probability of exactly 40 counts in a period of 60 seconds. Okay, so this is the first sort of question they ask us, and they change the time period. So now we're looking for 40 exactly, wasn't it? Exactly the probability we're looking for, isn't it? Exactly 40 counts in 60 seconds. Okay, so we've got to change our time period here, so let's do that first. So what do we know? Our lambda before was 3.4 in 5 seconds, wasn't it? Well, now we're going out to 60 seconds. Yeah, so we've got to multiply by 12. So our lambda is going to be multiplied by 12 as well. And we're going to end up with 3.4 times 12 is 40.8. And we're now looking for probability, so excuse me, let's just change that, let's hop that back in those moments where I didn't want to write that. So what we now need to write is we've got x with Poisson with lambda equals 40.8, and we're now interested in probably x equals 40. So we're going to use our PPD function button here on our calculator. So let's whiz back up, exit out of there to get us back to distributions. Poisson, PPD. We're now looking for 40, aren't we? In a period of 40.8. There we go. Press our XE button, and then we get, so here we get 0.625, 4 decimal places, isn't it? 0.0625. Quote everything to 4 decimal places, please. That'll keep you safe from MEI markers. Okay. Next step. Use a suitable approximating distribution to find the probability of at least 40 counts in 60 seconds. Okay, suitable. So we've got to decide which one's suitable. 5. Suitable approximation. Approx. We've got a choice between binomial and normal here, haven't we really? But we're really looking at normal, aren't we? Normal. And the useful thing here is if I just draw a quick diagram of what we've got, if we're looking at our normal, we're pretty close here to the mean, aren't we? Because they asked us here, we've got 40 is our x value, isn't it? This point, and our mean here is 40.8. That's going to be mean, isn't it? Now, what's our standard deviation going to be for our normal? If we're approximating, well, standard deviation is the square root of 40.8. There we go. So if we were approximating with a normal, we'd be looking at a normal. We need 2 things here, don't we? We need the mean, that's 40.8, and what else do we write in there? We use our mean, and we write our sigma squared here, so our life's easy with 40.8. Now, trick is to watch out for the last part, to push up a bit, is, remember, we've got to do our continuity correction, because continuity correction, isn't it? Because our Poisson is discrete and our normal is continuous. So what actually would fit into our window for continuous? Well, the one below it is 39, isn't it? So the area we're interested here is the probability of at least 40. Is what we're looking at. So in normal terms, we'd be looking at the probability that x is greater than, and our midpoint here, isn't it? Between the 39 and the 40. So we're looking at 39.5. There we go. Okay. So we're interested in this area here, all the way from 39.5, aren't we? That's our probability that we're interested in. Okay, so let's whiz our calculator onto the screen, exit up, so we get to the menu with the distributions. We're now interested in a normal distribution. I'm always interested in NCD and normal, aren't we? So what's our first item we're going to put in here? Well, our lower bound is 39.5. There we go. Our upper bound, good. Our upper bound is 99999. We just want to put a very large number. Oops, sorry, I don't want to do that. I want to go down one to the next one. What's our standard deviation going to be? Well, it's the square root. There's our square root button of 40.8. There we are. And our mean is going to be 40.8 as well. So let's press the XE button. And what do we get out of this? We've got a probability here of 0.5806, haven't we? 0.5806. I would quote it like that and leave it with 4dp. I don't think it's as reliable as that, but it was remarkably reliable because I did the Poisson calculation and it came out as 0.57. So there we are. How far are we going? That's another, how many marks did we get for that approximation? We just got ourselves another 5 marks and we've been running 12 minutes with me explaining everything. So we're really flying along so far, aren't we? Okay, final part then. They've changed the time period. What's the last thing they can change? The last thing they can change is by combining distributions. So what have they said to us here? We've got our source here, didn't we? Source has got radiation count of 33.4 counts per 5 seconds, wasn't it? 5 seconds. And they've now asked us, let's go back to the question, so if I skip past it, the background radiation rate also independently follows a Poisson, which produces a mean count rate of 1.4 per 5 seconds. What are they going to ask us to do? Find the probability that the radiation source together with the background gives a total count of at least 8 in the 5-second period. Okay, so first thing we've got to do, so they've told us that the background count is 1.4 counts per 5 seconds. So what do we do in Poisson? Poisson, we add the means, isn't it? Poisson, the mean of the combined equals the mean of the first plus the second. So our combined mean is just 3.4 plus 1.4, which is 4.8, which is as we'd expect, really intuitively, isn't it? That if we're getting 3.4 counts from the source, and we're getting 1.4 counts on average from the background, then overall we're getting 4.8 counts per second, for 5 seconds rather, and that's going to be our new combined lambda. Okay, what did they ask us to find? Probability that our hits of this combined are at least 8, so that's probability that it's greater than or equal to 8, isn't it? So what are we going to have to do next? It's going to go a bit too far there. Let's do our number line. We could have had 0 hits, 1, 2, 3, 4, 5, 6, 7, 8. Let's just put 6, 7, and 8 here. Right, at least 8 is this area here, isn't it? We can't get that out of our calculator, so we're going to do our complementary probability, which is that one there, and we're going to do 1 minus that, aren't we? which equals 1 minus the probability that combined x is less than or equal to 7. There we go. So let's work this one out quickly, which is 1 minus, let's get our calculator out. Here we go again. Exit, exit, distributions, binomial, and we're into BCD here, aren't we? Because we're looking for the cumulative value here. Okay, let's work down. What's our target number of occurrences is 7. What's our mean? It's 4.8. So here's our value, 0.8867. It was rounded to 4 dp, and that gives us an overall figure of 0.1133. There we go. So 15 minutes there with me jabbering a lot, taking us through the whole thing, and we got 3, 8, 11, 16, 19 points out of. So we're still we're running ahead of our target there, aren't we? Here we go. Okay, here's my final summary for Poisson. Remember, the rules are it applies where there's a constant rate and there are independent events. We find our lambda from the average or mean for the period specified. We use our standard number line approach to work out our probabilities using the PPD and PCD function on our calculator. And remember, if it's greater than or equal to a particular value n, you want to do complementary probability 1 minus probability x is less than or equal to n minus 1. If they adjust the time period, you just scale your lambda up or down. And if you combine Poisson variables, well, you just add the lambdas together and follow the same process of calculation. Hope that's of use.